Okay. Good morning, everyone, or good afternoon, I suppose, depending on where you're at in the world. Thank you for joining us for a presentation on our WENZEL CORE system and how you can use its optical scanning technology to measure your turbine blades. My name is Scott Romain. I'm the Regional Sales Manager for WENZEL America, and I'm very excited to be joined by a blade measuring guru, Mr. Henri Bosch. Henri, could you introduce yourself, please?
Good morning, good afternoon, good evening, everyone. As Scott was saying, wherever you are around the world. My name is Henri Bosch. I was born and raised in the Netherlands, went to school there, graduated college in 1990, and joined a company, a CMM company, and have been in the industry ever since. So 30 years of metrology experience in the various applications, not just blade measurement, but automotive, aerospace, medical, you name it, I've seen it. Thank you, Scott.
Yeah, no problem, Henri. Thank you. So today in our presentation, we're going to go through basically 3 steps. I'm going to tell you a little bit about the core. We're going to watch a video of the core in action, and then we're going to spend most of our time with Henri discussing why is the core your solution, you the customer. So with that said, let's jump into it. What is the core? Well, the core is simply an optical CMM with a rotary table. It's been in the market for 10 plus years, and it's calibrated via ISO 10360, just like any other CMM. Really needs to be thought of that. It does trade a optical probe for a touch probe, but in the basics of the machine, it is a CMM. We have 2 different size systems. The one on the left is a Core D. This is great for smaller turbine blades, smaller parts, up to about 300 millimeters tall. And then if you have anything bigger than that, we have the Core M, which is the big brother, and that goes up to 2 meters. So between a very large low pressure parts of turbines to very small high pressure parts of turbines, we have a system that can measure your part. So I touched on that a little bit. It is an optical CMM. Well, how does that work? What the core is doing, it's combining 2 technologies together to give us kind of the best trade-off between both worlds. You know as well as I do that some optical systems can measure down to nanometer resolution, but typically the optic will have to be incredibly close to the surface of the part, within a millimeter or 2. With the core system, we're using triangulation, which is 2 cameras and a dot of white light to give us a fairly large standoff distance. So the sensor can be up to 80 millimeters away from the part. We're combining that with peak intensity measurements to give us the absolute center of that dot. So that's where we get the accuracy of plus or minus 4 microns. Being far away from the part is important because this machine is incredibly fast, and to move the part fast, you need to be away from it to minimize the risk of collisions. It needs to be accurate, that's where the peak intensity comes into. So if we go to the upper right of this slide, I've got 3 bell curves drawn out. So how does this peak intensity work? So if you look at the red one, that's typical of the sensor being maybe perpendicular to the part. Go down to the blue line, maybe that's 45 degrees off off perpendicular, and the green line anywhere from 5 to 25 degrees off of perpendicular or off of the surface. So you can see that the curve itself gets stretched out, but the optics and the sensors inside are only looking for that peak value. So regardless of 5 degrees off the surface or perpendicular to the surface, we're still getting very, very accurate measurements within that plus or minus 4 micron envelope. So those 2 technologies that I've talked about, what does that get you? So I put a myriad of parts up here. Like I said, if you go to the upper left here, all of these low pressure, large blades can be measured on the Core M, all the way down to the very, very small high pressure blades measured on the Core D. With the peak intensity being so small, looking really at the center of that dot, we can measure knife-like edges. So down here in the bottom, these low pressure blades, the trailing edge of these is incredibly sharp, like almost enough to cut you. And the system has no problem with that. And Henri will touch on that a little bit later. Also, like I mentioned, it's a CMM. So there are blade-specific measurement tools out there. They may only be able to measure blades or blade features. This machine not only can measure the blades, it can measure prismatic features. So if we have, I put this little red circle up here on the upper right, you have these fir trees, these dimensions here, or these ceiling edges. all of that can be measured with the same system. You just put it in front of the sensor and measure it like you would dragging a probe, any type of probe. So now that you've got a bit of an idea of how it works, let's take a look at the core in action. So I've got a small video here. This would be the operator's perspective. And you can see it has a door open on the right and closed on the left. It is shop hardened. The doors are automatic. They can be automated to put this in an automation cell. But this is what the operator is going to see. Unfortunately, it doesn't really do the system justice because we can't see what the camera is looking at. So with that in mind, here's a view from the optics perspective. This is inside the machine. This is what the machine's seeing, and this will give you a better idea of that dot of white light I'm talking about, because it's kind of abstract. And remember, you can see the dot on the surface, and it looks a little big, but remember that the machine is looking for the absolute center. It's getting that true surface data. So as this video plays, Henri, you wrote the program for this. We're going to look at the program a little later in the software. Why don't you give us a rundown of what the machine's actually doing as it goes through this?
So obviously for any part measurement, a datum structure is required. So what it does is it's measuring a datum A, a datum B, and a datum C feature here. So it's scanning this plane and makes that datum A. And then it measures the two diameters, the two large bores, and it basically uses those two to create a datum B feature, which is basically a rotation. And then one of the two is an origin. And then what it does is it goes in and is now actually scanning one of the sections, the bottom section. And before it starts to scan, it actually establishes the exact location of the actual part. One of the biggest problems in metrology of blades is that leading and trailing edges that get very sharp cause overlapping areas when measured with a regular ruby kind of stylus. But in this case, what it does is it actually establishes the location of the actual section. And because we are measuring surface data, we're not compensating anything because the probe radius is 0. We're measuring exactly on the surface and never end up with any overlapping areas on leading and trailing edges.
I notice also. Go ahead.
For this
Sorry, Henri.
presentation, it's actually also measuring a couple of diameters, those small little diameters, just to show the possibilities of mixing prismatic data with airfoil-specific data.
Sure. So when you were talking about finding the actual position of those sections, on this blade, it's not very twisted or funny shaped, but I assume that's very important when we get into some complex blade geometries to make sure we follow the actual profile and not just a straight path across the blade. Is that true?
That is true, yes. So it is important, like I said, to make sure that we're measuring where the actual sections are versus where the nominal definitions are for it. So we go in and sample the part before we actually start to scan to establish a local alignment. This is a built-in function on the controller of this machine.
So you're not actually doing the programming for that, it's doing it automatically.
That is correct. As soon as in the program, you basically tell it, I want you to measure in blade mode, and it will automatically use this algorithm to do that.
Okay, so we're going to see that in a little bit. So this is where I want to transition actually to you, Henri. I want to talk to the customers about why the core system is their solution. And I think you touched on it a bit, where we're finding the absolute location of the section. We're also finding that edge. So I think you have an example brought up already on your PC of what that means to measure those sharp edges. So if you could just transfer us over to Henri's PC, and we'll take a look at the software. Ah, those look like sections. And Henri, I've lost your audio.
Yeah, so this is a typical example of a blade with very sharp leading and trailing edges, and the system is automatically adjusting for the density of the points, and that's what I really wanted to illustrate here. So I'm just going to zoom in a little bit on one of these sections. And what you'll see is that, so as a programmer, you basically tell it what the maximum distance is allowed to be between individual points. And because there's a very small amount of curvature on the concave and convex sides of this blade, so what happens is that the distance between the points automatically goes up to the maximum allowed distance on the concave and convex sides of this section. But as you can see here, this is a typical leading edge example. The density of the points is automatically increased on the leading and trailing edges. And again, this is a function of the controller. So the control actually knows, based on the scan path, the definition of how we want to scan this section. It knows where the transition, the curvature of the section becomes very tight. And so on a leading and trailing edge, obviously that is the case. So it automatically increases density along this leading edge. And then notice that it goes back to the maximum allowed distance on the concave and convex sides. And so that's on the leading edge, and the same thing exactly happens on the trailing edge as I go to this side.
Now I can assume that obviously we want more data around the smaller radii, but tell me a little bit more about why that's important to have that automatic feature in there.
So one of the important things on a blade is that the leading and trailing edges want to be as round, as circular as possible to reduce the amount of turbulence generated around the leading and trailing edges based on imperfections. And so what you can see here is that when in the manufacturing process, it's rather hard to get this nice and round, to get this nice and exactly round. And so you'll always see some imperfections on leading and trailing edges. And the great thing about the core is that it doesn't filter this away. It actually shows you what the shape of that leading and trailing edge is because of the zero probe radius.
Can you explain that a little bit more for me with the zero probe radius? I don't think I do a good enough job explaining it with it. It's looking at the center of that dot, but how does that compare to a probe?
So imagine having a stylus, a typical Ruby stylus that is used for most measurements on CMMs, on conventional CMMs. And if you imagine a Ruby ball of 1 millimeter, this is about a 3,000th radius here. So imagine a Ruby ball of 1 millimeter, 40 thousandths. And as it rolls around this leading edge, it cannot capture the little details that you see here, these divots and spikes, and it smooths it as it goes around it. And as a result, you're not getting the actual surface data. You're getting mechanically, if you want to call it that, physically filtered data.
So you could be manufacturing blades that you thought were very smooth and efficient that actually have these little imperfections. So you think about that over, I don't know, maybe hundreds or thousands of little blades inside of a turbine. Those little efficiencies all add up.
Absolutely, and the efficiency of the engine, it definitely has a negative effect. Performance-wise as well as fuel consumption-wise.
Yeah. So you've showed us these little sharp edges. I'd like to kind of circle back. The video we showed is of a program running. I was wondering if you could bring that program up now that we know about the point density, because our example part isn't really blade-like. It's kind of round, but yeah, and maybe show them this program running from your view in the software.
So just to show you real quick here, so here's the machine. I'm physically connected to the machine. And so what I'm going to do is I'm going to actually run the program that you saw in that video. So we'll just start and run it. So it does
again,
exactly the same.
Yeah, talk us through this again.
So right now it's scanning that datum A and creates a primary datum. I don't know if you saw there was a slight shift on the CAD model, meaning that the physical part is slightly angled on the machine. And so it creates a primary datum on that face. And then it does the two diameters, the bottom and the top, and creates a secondary datum. And then the top diameter in this case is the actual origin feature. And here it goes and does a scan, the bottom section first. And as you can see, the bottom of the screen, you can actually see what the cameras are seeing, or what the camera is seeing, I should say. So the camera looks at the projection of the light on the surface, and the top and bottom camera are basically picking up on this projection of that light.
It brings up a question, Henry. It has two cameras. What if you were trying to get those the cylinders or the plane down there, and one of the cameras was blocked by a part of the part.
Hmm. Well,
Can it still measure?
there's a calibration routine that it takes about 2 minutes, 3 minutes that calibrates the head, and basically any angle of the head is at that point calibrated, as well as the individual um, cameras. And so in that case, it doesn't matter whether one is blocked or not; it still does a correct measurement.
Maybe touch on this a little bit later, but I did notice you're doing the blade sections and the prismatic features all together, so that's interesting too.
And as you can see, it's a single program that basically includes the prismatic features as well as the blade-specific features. And so you can combine, in a typical CMM report, you can combine the prismatic as well as the blade-specific dimensions in a single report.
So Henry, now that you've showed us how it can adjust the point density and how it can gather this data, I'd like to kind of touch on, okay, what do we do with that data? How do we evaluate it?
So we have a blade-specific module built into the software, and it basically takes that nominal and actual information and performs, based on customer specification, it performs a best fit and then does a profile analysis, as well as thickness evaluations. I mean, very commonly on blade sections, leading edge thickness, trailing edge thickness, maximum thickness, cord length. I mean, these are all dimensions that are quite critical for, again, for the performance of that specific part that gets mounted in this engine. And so if I go back here real quick, so what we have is in the blade module, for every blade, for every section, we have different settings. Different manufacturers have different specifications when it comes to these kind of dimensions, like leading edge thickness and trailing edge thickness. And so a very common way of doing leading and trailing edge thicknesses is by the 95% rule, which is 5% from the leading edge and 95% from the leading edge, which is basically 5% from the trailing edge, is a very common methodology. And you can see here a little graph that shows you, it's this percentage of the total cord length that is used, at which point the thickness is calculated. But as you can see up here, we also have an edge length. This is just a different evaluation, a different methodology for evaluating the leading and trailing edge thicknesses. Or we have a stacking axis length. And these are all implemented based on customer input. Various customers have different requirements, like I said. And so we've implemented all these based on communicating with our customers and looking at their needs and putting these different evaluation methods within the software.
So if I was a supplier to a big turbine manufacturing company and they were requesting that I have to evaluate my data in a certain way, you're saying that we probably have worked with them and we have it, and if we haven't, then we could implement that?
That is absolutely correct. Many of these specific dimensions have been done in that way. To give you an example, if I just look at this section here, we have things like, and like you said, this is not really a good example of an actual blade, but we have things like wrap angle. This is one way of looking at a characteristic that's very specific to a manufacturer. The BE distance, which we call the camber depth, which is basically a dimension, again, it's very specific to one manufacturer. We also have, as you can see here, we performed a least squares best fit in this case, but we also have different ways of performing other best fits. A very uncommon one that we actually implemented not too long ago for one of our customers is the circumscribed and inscribed best fit, which is very similar to a guillotine gauge type of analysis, where, imagine a hard gauge, and you put a blade inside the gauge, and you close two knives, and these two knives are in the nominal shape of the blade, and they will come and touch the blade on concave and convex sides, and of course, they are linearly hitting the blade, so they will hit at the highest point of the blade, which means there's going to be a gap in the non-highest points of the, between the knives of the guillotine gauge and the part itself.
Yeah.
And so that's what this, circumscribed best fit does. It actually simulates like a guillotine gauge for the best fit methodology, not for the measurement.
Interesting. And that, again, was not in the software. A customer needed it, and so we implemented it.
That is correct, yes.
Neat. So now that we've evaluated this, and it's interesting because basically everything we've said so far is based on customer feedback. So we can evaluate this data that we've collected based on their requirements. So what do we do to tell them about it? How do we report that out?
So I don't know if you noticed, but when the program was done, it actually generated a report. And so what we've done in this case, in this program, is we've actually created a numerical report, and I'm just going to scroll up here, that actually shows you the bottom diameter, the bottom diameter that it measures for the datum, then the top diameter that it measures for the datum. And then if I scroll down here, notice that here are some blade-specific dimensions. Here it says, here's the leading edge radius, trailing edge radius, etc. for section AA. And it basically gives you a numerical representation of that specific section and its leading edge information. Now, in addition to that, it's also generated a very specific blade report. So in a lot of cases, and I'm not saying everyone, but in a lot of cases, the customers are interested in just numerical data. But once they see something that's out of tolerance, they may want to go and look at the actual form error reports or the graphical reports to find out, what happened with that? Why is that section out of tolerance? And so as you scroll down in this report, this is what we call a blade summary report. So if you start from the top, the first page shows the three sections. Of course, if you have more sections, then it will show more sections. And it just shows a quick overview of what the dimensions look like for that specific section. And as you scroll down, it goes and drills down into the individual specific section. So here we got section at Z 40 millimeters in this case, and it shows you all the detailed information, the profiles, etc. It shows you what the tolerances are, and then of course it shows you here whether you're in or out of tolerance and by how much. It shows the best fit results. It says, okay, well, we did a best fit for this section, and these are the results of the best fit. We're out by this much or we're in by this much. Obviously, in this case, we're in tolerance. And as I keep going down, obviously, you're going to see the other sections. Here's the next section. I'm going to scroll down quick. And then we get into the actual form error of that section. So here you can see that the leading edge on this first section is out of tolerance. It's short. And like I said, this is not an actual blade. This is like a demonstration part, but it gives you a very good representation of what it would look like. And then here we have the trailing edge, which looks in tolerance. And then it does the same thing for the other sections. So this is one report. But in a lot of cases, customers may have specific report requirements. So I made a little, we have templates, and these templates give you the ability to, this is the summary, excuse me, let me go back to this one here. So sometimes all that information is not necessary. If they already have a numerical representation in the numerical report, maybe they just want to see profile in the report. So in this case, we created a template for this specific customer that shows just the profile report because they already have all the numbers. And so again, you can see here, this report just has the concave convex sides, the leading and trailing edge for each section, reducing, of course, the number of pages and give it a very quick review of what might be happening with that specific section.
So this is following along with that same philosophy that we did with the evaluation methods. If a customer needs a report to look a certain way, we have the templates in there, but what if they're not in there? What if it's something strange that we don't have a template for?
So we have a template builder. It basically allows you to take any existing template and modify it to your needs. In some cases, or in many cases actually, we actually do that for the customer because we obviously know the product very well, and we know exactly how to create or edit templates. And it's a very quick process. It's just a matter of editing an existing template or creating your own.
So it's a nice feature, though. You can have us adjust that to what you need, and then once it's done, for the most part, the customer can just hit the button to report, and it's going to look exactly like they need it for the rest of their parts. Yeah.
Exactly,
So
yeah.
with you showed us, I want to come back just a little bit. We're about 5 minutes out here. You showed us a blade report, and you kind of had a regular CMM report, and I've said to that it is a CMM, but maybe we can go a little bit on programming, the full part instead of just the blade.
So this is the program. This program right here is basically the measurement of the datum features, as I said, datum A, and then the two diameters for datum B and C. And then in the same program, we scan the sections. So if I scroll down a little bit here, down a little bit more, and right here was basically creating scan paths, and we're scanning the sections, and then down below that, we actually do the analysis. So the actual evaluation of all the blade specific dimensions.
So forgive me, Henry, I know I'm just a sales guy, but that looks like an awful lot of code, and I see some buttons down there in the bottom. So if I'm measuring a blade and I also have, like you said, there was that plane and those circles that you measured, can I just use it like I'm on a CMM and just click the button and say I need to measure a circle?
Absolutely. So you basically go in and use the tools available right here from this toolbar to pick and choose whether you want to do a two-dimensional feature like a circle or a line, or whether you want to do a three-dimensional feature like a cylinder or a surface. And you just tell it that you want to scan it in a certain methodology, and that gets created into the program.
And if I want to, do I have to wait until the very end of the program? Can I just put it in wherever I need to?
Yes, obviously, you know, from an editing or program creation standpoint, I can put my cursor anywhere, and I can start recording right in that position, and I tell it what it is I want to measure. So I can always go back and edit the program. I also have a regular editor where I can basically edit the program like a text editor.
So you can go the easy way like I like, or we can go the very detailed route like you like.
Yeah, that's well said.
Yeah. So Henry, I really appreciate you hanging with me on this presentation today. Is there anything else that you have in mind or that you'd like to say about the software or the machine?
Well, what I can say is that our customers that have the core system are very satisfied. It's a very robust system. It's shop hardened. It's very reliable, and I'm just very happy to deal with the customers that have it and are very satisfied with it.
Well said, Henry. Thank you very much. So I guess with
Thank
that, yeah, thank you. With that, I want to thank everyone for joining me and Henry. Henry, thank you very much for your insight in this, and I hope everyone has a wonderful afternoon.
Thank you very much for joining.